We are here at the high-tech campus in Eindhoven. With the help of the province of North Brabant and the Ministry of Economic Affairs, we have been able to build a pre-pilot line for batteries. We all know how important batteries are for the energy transition. Driving our electric cars, we want to extend the range. If you have a mobile phone, you don't want to charge it every day. So we really want to enhance the performance of our batteries. If you look at the companies in the Netherlands, they are focusing on materials or components of these batteries. That's their business. And what we can add to that is how to integrate these materials in battery cells. So actually making the whole system working as good as possible and giving them feedback on the materials they are developing. So we can really help these companies to keep their focus and to speed up the developments towards the market. A lot of developments are ongoing for a next generation of batteries with much better performance. Think about performance of energy density that can be raised by 100%, which opens new applications, for instance in aviation. But also other developments that make the batteries more safer or allow you to use a higher charging speed. So all these issues are really important for making the energy transition possible.
Our partners usually focus on improving a single battery component's performance. Then they need to prove the performance of this material in a larger scale, which is a pouch cell scale. Usually the challenge that they have is they cannot find matching performance of the other battery components, whereas the Holst Centre has connections over the world to provide these sort of materials, and then we work on integration of our customers' materials with matching performance battery components. We prepare our pouch cells in glow boxes which have protected atmosphere. We can start by taking electrode films, we cut them in specified dimensions. Then, using our ultrasonic tab welder, we weld the tabs. Then, we stack the electrodes with the separators. Then, we insert them in a pouch, we fill it with electrolyte, and as a last step, we seal the pouch cell all in a single glow box. When the cells underperform, we have ways to understand why it died sooner than it's supposed to. We can use some post-mortem analysis such as X-ray photoelectron spectroscopy and scanning electron microscopy. These tools help us understand, help us derive some conclusions about these, which we can give as a feedback to our customers, then they can work on improving their materials.
Charging speed is an important characteristic of batteries. We see it when we charge our phones, our electric vehicles, all kinds of technologies, and we always want the charging speed to be faster. So you can achieve this a little bit by changing materials or materials properties, but we think that a substantial difference could be made by using 3D structured electrodes. So at the TNO Holst Centre, we have a long history and competence around thin film depositions. So using that competence, we can make, for example, carbon nanotubes. We make these carbon nanotubes using chemical vapor deposition, and we can grow these CNTs into different shapes, morphologies, and we can create different three-dimensional structures like that. Then we have some surface area enhancement factor with these CNTs that leads to potentially higher charging speeds.
One of the biggest challenges with the conventional lithium-ion batteries is safety, which is because of the flammable liquid electrolytes inside the battery cells. A nice alternative is all solid-state batteries, in which we replace this liquid electrolyte with solid counterparts which are non-flammable. We produce battery components for these all solid-state batteries using the extrusion technique. Extrusion is a technique which can revolutionize battery production. Next-generation electrodes and electrolytes can be produced using more sustainable materials and without the currently used toxic solvents. We are working on developing expertise on fluorine-free binder materials that can be used in the electrode production.
In order to achieve a lot of the parameters that we've discussed here, like higher energy density, higher charging speed, safety, etc., you incorporate new materials and new concepts. But it's not obvious that when you make all of these individual components that they will be compatible in a battery altogether. So to mitigate this, we use spatial atomic layer deposition, And we use that for interface engineering. So we make very thin layers in between these components, let's say between the electrode and the electrolyte, in order to enhance their electrochemical and chemical compatibility. We can curate this solution towards different chemistries, and we can make different kinds of layers on both 2D and 3D structures. And we can even use these layers to increase the moisture stability of some materials so that they are more compatible with dry room conditions. So with the prepilot line and our technical competence, we aim to help companies by integrating their components and solutions into a working battery. And so with that, we hope to accelerate their progress and to help them hit the market sooner.